All science can be seen as a search for unity. By discovering deep linkages between different physical phenomena, the scientists can construct simpler yet more powerful descriptions of reality. The subject of subatomic particle physics is full of these unifying connections, but how far can this process go? Can we envisage a final theory that brings all things together in a single mathematical scheme, or is this intellectual arrogance? Paul Davies, the end of the day approaches, along with the end of a century, and indeed a millennium. Millenarian and apocalyptic theories abound. I've bumped into any number of messiahs. Academics tell me it's the end of history. Others tell me it's the end of ideology. Are we perhaps reaching the end of physics?
There is a feeling abroad in the physics community that we're approaching some sort of culmination, some sort of drawing together of the threads. Now, this may be an illusion. It may be that in another 10 or 20 years it'll all fall apart again. But I think there is some sort of evidence that at least part of our understanding of the world, the microscopic part, is coming together into some sort of unified theory.
Well, let me prevent premature ejaculation on this issue and let's have a potted biography of the sequence of events. Let's go back to the Greeks, which is always a good point to start.
The idea of unifying knowledge, unifying our understanding of the physical world, is a very ancient one. It goes right back to ancient Greece, to the early Greek philosophers who puzzled over such things as permanence and change, of being and becoming. They couldn't understand how a world of objects that retained some sort of identity could change into other objects with different identities. And one way of solving this problem was called atomism, the idea that beneath the complexity and diversity of physical forms and systems that we see around us in the universe lies a pleasing and harmonious simplicity, that everything in the universe is put together out of a few simple, basic building blocks, and that everything that ever happens in the universe is simply the rearrangement of these building blocks. They called the building blocks atoms, and at the time there was no way in which they could check this hypothesis. It took 2,000 years before science began to provide ways of examining matter on a sufficiently microscopic scale that the evidence for these atoms could be uncovered. And now in the 20th century we finally believe that there are things called atoms. But what we call atoms today are not the elementary building blocks of the ancient Greeks. And the reason is that the essential quality of these Greek atoms was that they should be indestructible. They should be primitive, truly primitive in the sense there are no bits inside them. But the things we call atoms today, we can break apart. They're composite bodies with components inside, such as a nucleus. And even the nucleus itself contains neutrons and protons. So there's a sort of hierarchy.
Paul, let me ask you this. There used to be a belief that we might be dealing with infinite regress. Has that now been disposed of once and for all?
I don't think you can dispose of that idea of infinite regress because it's at any given time, science can only probe to a certain scale of size. And at the moment we can look at structure on scales about 1,000th of the size of an atomic nucleus, perhaps a bit smaller than that. But it could be that if we could get down to some still smaller size, we would discover a whole new world of complexity. But there's a sort of act of faith among physicists that as you break matter apart and get down to smaller and smaller scales of size, so things ought to get simpler and simpler. I might say that just as a historical note, I can well remember when I was a student in the 60s that this was a rather bad time for this whole program because atoms have been, of course, well known for 100 years. The existence of the nucleus and the neutrons and protons has been known for 50 years. But there seemed to be a whole proliferation of other subatomic entities. The so-called atom smashers, particle accelerator machines, were churning out new particles almost daily. In fact, they ran out of names for them. They had to invent Greek letters and so on. So all these particles were appearing, and nobody had a clue as to what they all meant or how they fitted together. It looked almost like a zoo, as if there was going to be sort of an unlimited number of different types of entities as you got more and more into matter. Then about 10, 15 years after that, it began to come together again because it was discovered that all these different types of subatomic splinters were actually related to each other, like members of a family.
You're talking about the forces now between them?
No, I'm talking about the actual identities of the particles. So we had this whole sort of shopping list of particles. Nobody knew quite what to do with them. And then they discovered that if they measured certain properties like their mass or electric charge or their spin and so on, they could be grouped together into families. Then some very clever people spotted that these families had the relationship between the members of the family were mathematical symmetries. Symmetries played a very important part in our attempt to understand nature, and we see symmetry around us, all around us in the physical world, but these symmetries in the subatomic realm are of an abstract nature, so they can only be expressed mathematically. But they're very distinctive. So instead of there being just a sort of random, arbitrary collection of different types of animals down there at the subatomic level, it looked like there was a sort of hidden order of a subtle mathematical nature having to do with these symmetries. So we have all these particles, but then there are some gaps, there are some that are missing. One of the fascinating things about this subject is the way the gaps get plugged. Again, if I can allude back to the time when I was a student, many particles being discovered and arranged into these pretty patterns and hints of underlying symmetries. And of course, some clever people such as Murray Gell-Mann, for example, were able to look at these patterns and say, hang on a minute, there's a gap there. There ought to be a particle to go in that gap. Go out and look for a particle with such and such a mass, such and such a charge. And of course, the experimenters went out and looked for these particles. Lo and behold, there they were.
So now we're talking about gravitation, electromagnetism, the four great forces.
Yes, these particles of matter, of course, don't just go about their business in isolation. They interact with each other. And there are four forces which physicists recognize as being the basic forces of nature. Now, two of these forces are familiar in daily life. There's gravitation, the good old Galileo experiment. We drop an object, hits the ground. So gravity keeps our feet on the ground. We recognize that in daily life. Then there's electromagnetism. Now, I should mention that 200 years ago, electricity was one force, magnetism was another. They were regarded as separate manifestations. And then the work of Faraday and Maxwell and others in the 19th century showed that electricity and magnetism were closely interwoven. Electricity can produce magnetism, magnetism can produce electricity. And clearly these are two components of a single unified electromagnetic force. So now we talk of electromagnetism as a single force. But it was the first example of the unification of two forces into one. So we have gravitation, we have electromagnetism. And then in this century, we've discovered two more forces, the so-called nuclear forces, which just have the labels weak and strong. There's a weak nuclear force and a strong nuclear force. So there are four forces: gravitation, electromagnetism, weak and strong nuclear forces.
And they're crying out for a grand unified theory.
That's right. If electricity and magnetism can be seen to be parts of a single electromagnetic force, why can't these other forces be brought into the scheme and be unified? In fact, as long ago as the 1830s, Michael Faraday in London performed an experiment in which he tried to show that there was a link between electricity and gravitation. He foresaw that there may be some sort of deep amalgamation possible. He didn't discover it, and it's an idea which sort of faded away and has come back into vogue. But there is an impression that if we were to live in a world with, say, four fundamental forces, that's a bit arbitrary. Why four rather than 14? It would be much easier to have one underlying superforce or master force that manifests itself in four different varieties.
Now, am I right in suspecting that there are some people who want to tie this up with string, i.e. these superstrings?
The superstring theory is just one in the latest of a long list of attempts to unify these forces, to amalgamate them into a single superforce. But it goes further than that, because quantum physics shows that there is a very intimate link between the nature of particles and the nature of the forces. You see, in everyday life, we would think that particles are lumps of matter and forces are things that push and pull between lumps of matter, and these are two quite separate types of physical thing. But at the level of atoms and below, what you find is that the forces operate through the exchange of other particles. Now let me explain, for example, the electromagnetic force. If we have electrical wire here with currents passing through, there's a magnetic attraction between them. It's very familiar. And this is normally discussed in terms of a magnetic field or something. But at the atomic level, the description changes, and instead we like to think of, say, electromagnetic forces as due to the exchange of, in fact, particles called photons related to light. And we can think of these photons as being messengers that convey the force. So if you have two electrons or two electric currents, one electron will send a messenger photon to the other one saying, hey, move. And so we can think of the operation of forces at the subatomic level as due to the exchange of these messenger particles. So we have one list of particles over here, the particles of matter, which are being unified into families. There are lots and lots of them, but we feel that there's some sort of basic building blocks there. And then we have another lot of particles over here having to do with the forces. Now, the great hope is that we can then bring about a further unification of the messenger particles and the matter particles into a single mathematical scheme, a single set of formulae that would merge together the description of the forces and the particles in one sort of super theory.
You remember that marvellous image from antiquity about the cosmos being carried on the backs of turtles, and there's a whole succession of turtles. It has been put to me by people more scientifically literate than I am, that in a way those turtles can represent tautologies, if you like, and that each new theory is a magnificent tautological expression of things that are already known. In other words, theories explain theories, or support theories.
No, I think that's wrong. I think that what happens with scientific theories is that when one theory replaces another, it describes more, it's more powerful, it's more encompassing.
A bigger turtle.
Yes, and the essence of this unification scheme is that with each step in the amalgamation of things, we reduce the total number of concepts, the total number of arbitrary features. We find linkages that didn't exist, just as Faraday and Maxwell found linkages between electricity and magnetism, and therefore reduce the number of entities that we need to have to describe the world, just as Einstein found a link between mass and energy and space and time. So these new theories are finding further linkages between aspects of physics that were previously disparate.
What I've always liked about your work is that you constantly talk and write about complexity, about the infinite complexity of this universe of ours. And yet here you're suggesting that there's another arrow, an arrow of simplification, of theoretical simplification, of growing complexity.
Yes, that's right.
Is that a paradox?
I don't think so, because we started out with this Greek vision that we live in a very complicated universe, and yet beneath it all is this pleasing and harmonious simplicity, that all the variety of different physical forms are simply due to the different atoms that they contain, arranged in different ways. And so this sort of downward path from complicated big things to simple little things is fundamental to the whole program of physics as it's been conducted over the last 300 years. And it now looks, as we approach the end of this millennium, that we might be on the verge of this final step, the culmination of this unification program,
Well,
of getting to the bottom level of
Forgive
reality.
me, Paul, but you know very well that claim has been made at various times in history.
Yes, it has. Yeah, but they
And
were
it's
wrong
always
in the
been
past.
hubris, hasn't it?
I think that there is some reason now for us to be fairly confident that we are glimpsing, if not a final theory, at least the bottom level of reality. You know, we started off by talking about these atoms, and then I said that what we call atoms today are composite bodies. They've got bits inside them. Well, what have they got? They've got the electrons, and then in the nuclei they've got neutrons and protons. And then in the 60s and 70s, it was discovered that even the neutrons and protons had bits inside them. We give them the whimsical name of quarks. And then you can conjecture that there are bits inside the quarks, and so on. And down we go like a whole set of Russian dolls. Maybe it's never ending. But I think that there is good evidence that with these quarks and the various messenger particles I've been talking about, and electrons and neutrinos and so on, that this shopping list of particles is, as it were, almost the bottom level of reality, that there isn't much further to go. Now, what we would like to suppose is that that there is one more level, that all of these particles whose names I've mentioned are all made out of some single entity, some primitive building block, something which is truly indecomposable, and which might not be a particle at all. It might be a little loop of string. So an idea which seems sort of ludicrous, but it's very fashionable at the moment, is that the Greeks actually got it wrong, that the world isn't made out of tiny particles, tiny indestructible atoms. It's actually made out of little loops of string that wiggle around.
There are many toiling in the vineyard of science, and many discoveries now seem to have a collective stamp on them. Yet again and again, the great breakthroughs seem to come from a single mind.
Yes.
Is there such a mind lurking in a lab or standing in a lecture room somewhere at the moment?
It's often said that what we need is another Einstein to draw all these threads together, because, as you can tell from our discussion, we're left in a rather unsatisfactory, tentative state where we can glimpse certain unifications, but we lack that simple magic formula that you can wear on your T-shirt that would encapsulate at a stroke all of the particles and forces of nature in a single descriptive scheme. And perhaps what it needs is someone to come at this with a totally fresh approach from a completely new angle and weave all this together in a way that doesn't require huge expenditure on further experiments.
But the name and address of this marvellous man or woman remains a mystery.
Oh, well, from time to time, various names and addresses are suggested. I won't mention them now, but I would say that there is nobody that at the moment seems to be coming at these problems with sufficient novelty and sufficient intellectual power to equal for particle physics and unification what Einstein did for gravitation and space and time.
Well, let's go back to the ordinary punter, who increasingly seems to suspect that TOE equals GOD, this equation. Now, this is, of course, an immense overstatement, isn't it? You're talking about a theory of everything which would illuminate further scientific inquiry rather than close it down, aren't you?
I think you have to be very careful with the use of this TOE label, theory of everything, because what do we mean by everything? Supposing we had this magic formula that I could wear on my T-shirt, from which by suitable mathematical manipulation we could correctly describe all of the fundamental particles and forces of nature, that we would have identified the ultimate building blocks out of which the universe is put together. Supposing we had such a thing, would it explain why people fall in love or why they vote in certain ways at elections or the movements of the stock market? No, of course not. Wouldn't even explain the origin of life or the nature of consciousness. We're talking here about the culmination not of physics. The end would not be in sight of the whole of theoretical physics. We're instead talking about the culmination of what we might call the reductionist program. Begun in ancient Greece, the idea being that we can explain the world by explaining the bits and pieces out of which it's made. If only we can break open matter at a smaller and smaller scale and find out the ultimate building blocks. If we understand those building blocks, we'll understand everything that exists. I think this is total nonsense. I think it's a very important part of physical science. The reductionist program has been immensely successful in helping us to understand the universe, but it's only half the story. Going the other way.
I'm glad you say that as a scientist, because there are many in the anti-science bush, and Brian Appleyard comes to mind, who would scream blasphemy, in effect, at this argument that the theory of everything is about to be unveiled and it is going to be the ultimate example of reductionism. Because, of course, reductionism is now the most lethal of pejoratives, isn't it?
Reductionism's had a bad press, and I think partly this is because people confuse reductionism as a method and reductionism as a total explanation, as a theory of everything. We better just explain what reductionism is. I mean, it is a way of explaining the world by reducing phenomena at a certain level of explanation or a certain level of description, reducing that to processes at a smaller level, smaller in size, or at least simpler in explanation. And so it's often said that biology is reduced to chemistry, chemistry is reduced to physics. So if you take a human being, you say, well, a human being is nothing but a collection of cells, and cells are nothing but a collection of chemical reactions, and chemical reactions are nothing but a collection of atoms and molecules doing their thing. And so ultimately human beings are nothing more than moving mounds of atoms. So it's a sort of obnoxious philosophy because it seems to devalue so much that is important to us. Yet as a methodology, it's extremely powerful. There is no doubt about it. Physicists breaking open matter and finding quarks and things inside, have made enormous advances in understanding the world. And that biologists, in breaking down cells into the genome and understanding the genes and the interaction between the proteins and so on, have made enormous advances in unravelling the mysteries of life. But it's simply a mistake to assume that that's got to be the whole story.
Or that it's a one-way street, because in a sense, fairly simple discoveries made it possible to build Gothic cathedrals. You know, so you may be able to, once you get this wonderful theory, to build on it in unimaginably complex ways.
Yeah, we often talk as though there are two counter-directed arrows. There's the arrow of reductionism going down to the simplest building block sitting here, and then the arrow of holism, which is going in the opposite direction to the collective and organisational holistic aspects of complex systems. But of course you can find linkages between the two. And for me, one of the most fascinating linkages is that the most complex system we know, namely the human brain, which gives rise to consciousness, gives rise to culture, gives rise to things like mathematics, can find its most convincing applications down at that bottom level, those mathematical symmetries that describe how matter is put together.
Which may be, as you said in an earlier program, the universal language.
Mathematics is the language of nature, and yet a product of the human mind. Isn't that fascinating? Isn't it incredible that something that comes out of this most complex system we know, something that is a cultural construct, nevertheless finds its most powerful applications to the simplest and most basic components of the universe? That's what I find marvellous and inspiring, that looping back of the complexity back into the simplicity.
I like it when you get excited, Paul. It's good to see you enthusiastic. Now, last night over dinner, I was complaining of the fact that in this enormous universe, with this almost infinite number of years available, I've got a wretched 600,000 hour lifetime, most of which I've already wasted and expended. And we were discussing how many years we'd think would be a reasonable shake. And we agreed we'd like a millennium. We wanted 1,000 years each.
Yes, I think we need 1,000 years.
Now, let's hope that you get your 1,000 and use it productively. If we were to have this conversation in 1,000 years' time, there'd be a slight modification to the landscape here.
Not much, I suspect. Yes.
Not a lot. What would science be thinking about in 1,000 years? Would it all be over? Would it simply be tinkering? Would it be fine-tuning? Or would there still be extraordinary prospects? Not for technology,
yes,
for theory.
That's right. It seems to me, looking back over my career, that we're living at a rather extraordinary time when the pace of discovery, the pace of events has been frenetic. It can't go on like that forever. But I come back to the fact that the reductionist program, whilst I believe that we might be on the verge of completing it, and that in 1,000 years we could open a textbook and there would be the magic formula, and you could go down to your local supermarket and buy the T-shirt with the magic formula on the front, that it would be fully recognised that that was not a theory of everything, and that when we move in the other direction, in the direction of ever greater complexity, there are ever more mysteries to solve. There's a whole universe out there to explore. There may be any number of complicated physical forms, physical systems that we could not explain just with that theory of everything. So I'm sure there's going to be a lot left for us to do, even in 1,000 years.
In that case, it's badly named, isn't it?
Yes, it's very badly named. It's not a theory of everything unless you're an out-and-out reductionist and believe that literally everything in the universe boils down to what individual subatomic particles or little loops of string or whatever it is are going to do.
I've always preferred questions to answers. I really do. I love the process of questing. Answers are exhilarating. But I must say, I would like to live long enough to hear this particular T-shirt item, to hear it expounded, and to see how far it does go to explaining the things we've been discussing. Would a theory of almost everything, if but heavily qualified, help us much with time? Would it help us much with consciousness?
No. Yes for time, no for consciousness. Because time is such a fundamental part of the physical universe. Time and space are interwoven. And as Einstein showed us, gravitation is a manifestation of the warping or distortion or curvature of space-time. Any theory that amalgamates gravitation with the other forces of nature has to take care of space and time as well. So we would expect of this theory of everything, or not quite everything, not only a description of all the particles and forces of nature, but it would tell us why there are apparently 3 dimensions of space, or maybe more, with some of them hidden, and how this whole thing came into existence in the first place.
And how it will end.
And how it will end. So it would be a theory of the fundamental matter and forces of nature and the origin and end of the universe, all in one marvellous formula or set of formulae, one textbook.
Go on, show us the T-shirt. No, come on. Show that the crew want to see the T-shirt.
Yes. Well, we've designed the T-shirt. It's the formula that we're having trouble with.
If we can conceive of a theory that unifies nature, at least at the microscopic level, in such an elegant way, it's but a small step to ask where the subtle mathematical scheme comes from. Of course, this entails leaving physics and plunging into metaphysics, but in our final episode, Paul and I will plunge and confront the ultimate big question. Does there exist some sort of meaning to the universe, or even, perhaps, a God?